How we doing, guys? We're looking at normal distributions in this chapter. So if you look at this histogram here, it shows the birth weights of a set of babies from this study in 2002. It's 3,226 babies have been measured. What we're most interested in here is that the average weight was 3.4 kilograms. And the standard deviation, if you remember, is a measure of how spread out your data is. And we saw how to calculate that on our calculators in the last chapter. We're going to call that 0.6 just for simplicity. That describes this distribution. If you say it has a mean of 3.4 and a standard deviation of 0.6 and is normally distributed, then you're describing it very, very well. And we can make a lot of predictions because all normal distributions have some characteristics in common. Now, what do I mean by normal distribution? Well, this black line here follows a kind of an abstracted version of what this histogram looks like. Okay, that shape there tells you how our data is laid out. And whenever you see that shape, that's a normal distribution. And in an awful lot of things in life, in biology in particular, so things like weight, height, IQ are often distributed like this normally. The fact that it has a standard deviation of 0.6 tells you how spread out this data is, and we're going to work with that now for just a moment. Okay, so we can describe individual babies within this study. Given that we know that the birth weight on average was 3.6 and the standard deviation 3.4 and the standard deviation was 0.6, if a child is born at 4 kilograms, we'll say what that is an average weight plus one standard deviation. Okay, that is 3.4 plus 0.6. Okay, and we'll describe them as having a standard score of +1. A child who is born with a weight of 2.8, well, that is 3.4 minus one standard deviation minus 0.6. That is one standard deviation below average, and they have a Z score or a standard score of -1. And we're going to have a rule that says 68% of any normal distribution, so in this case, 68% of these babies born will have a Z score between minus and +1. Or are born within one standard deviation of the mean. Okay, and what does that mean? It means their weight is between 2.8 kilograms and 4 kilograms in 68% of cases. And if I was to tell you that a child had a birth weight of 2.2, well, that'd be 3.4 minus 2 times 0.6, or 3.4 minus 2 sigma. So that'd be a standard score of -2. Or they're 2 standard deviations below the average birth weight. Okay, so how do we calculate that Z score? In general, the rule is you take the actual value, you subtract the average value, and divide by the standard deviation. So for 4.6, that'll be 4.6 minus 3.4 divided by 0.6. That gives 1.2 over 0.6. That's a standard score of +2, or this child will be 2 standard deviations below average, above, because the positive standard score. So again, there's a rule: if 68% of values on a normal distribution lie within one standard deviation, 95% of values lie within 2 standard deviations. So in our diagram, we'll say 95% of the birth weights are between 2.2 and 4.6 kilograms. Okay, let's just go back and have a look, see if just intuitively, if that makes sense. Okay, so here's our diagram. There's 2.2 is around here, 4.6 is over here. So 95% of our birth weights lie within those two values. That kind of makes sense. I think 95% of the babies in this survey have values between 2.2 and 4.4 for their birth weight. Okay, and the final rule is that 99.7, or basically everyone, will be within 3 standard deviations. That if you're in a normal distribution, it's very, very unusual to find any values outside of 3 standard deviations. So in our case, that's 3.4 plus or minus 3 times 0.6, or 3.4 plus or minus 1.8. What's that going to be? That's a high of 5.2 and a low of 1.6. Okay, so that's our range of values. And we say the empirical rule says 99.7. Sorry, that's what this is called, the empirical rule. This is kind of a rule of thumb that we use. 99.7% of values will lie between those two. Okay, so 5.2 there, you can see almost none of the birth weights are 5.2. 1.6 is around here. So there are actually some birth weights below 1.6. And you can see that really this little section here doesn't fall underneath that theoretical black line that we're using to describe this normal distribution. So when we use a normal distribution to describe real life events, there's always a certain amount of approximation or matching data to a particular curve, what's called a bell curve in this case. Anyway, our normal distribution in general will follow this empirical rule. It's given there on page 296. 68% of values on a curve or on a histogram will lie within one standard deviation. And within that, actually, you can see that 34 or half of 68 will lie between the average and one standard deviation above. That these are symmetric distributions, that you have the same number of, in this case, babies of a particular birth weight that are above average or between average and plus one standard deviation, as there are below average or between average and minus one standard deviation. Okay, same rule tells us that 95% of values on a normal distribution are within 2 standard deviations of the mean, and 99.7% of values are within 3 standard deviations of the mean. So using our empirical rule here, to estimate the percentages in each of these diagrams, in each of these curves. And it is just an estimate. And our empirical rule, by the way, only holds for standard scores that are 1, 2, or 3. So you'll often have a standard score of 1.5. We'll see in the next exercise how to deal with standard scores that are not whole numbers. And this is just a rough rule of thumb. Right, this first diagram here, you're talking about data that is distributed between plus 1 standard deviation and minus 1 standard deviation. So that our empirical rule says 68% of data is going to be between those two. So percentage of all values in the shaded area, 68%. For the second diagram, within 2 standard deviations, the empirical rule says 95% of our data is between plus or minus 2. Our third diagram is a little bit different. I'm going to draw that separately. Okay, for our third diagram, you can see we have a standard deviation, 1 standard deviation below and the mean. Well, that's half of our 1 standard deviation rule. So that's half of our 68%, is 34% of our data is contained in this side of the diagram. And between our average value and 2 standard deviations, 95% is what our empirical rule says. We're looking at half of that, which is half of 95 is 47.5%. So contained within this, you'll say 34% plus 47.5% is 81.5% of our data is contained here. And this is really useful because later on we'll be able to say, well, between any 2 particular values or any 2 particular weights, you can predict how many members of a particular population will lie within them. So this has a very strong forecasting value, which is really what statistics aims to do, is to describe but also to predict patterns in large numbers in populations. And part 4 here, well, 64 is 4 higher than 60, which is 1 standard deviation. Okay, the standard deviation in this diagram is 4. So that's 1 standard deviation above the mean. 56 is 1 standard deviation below the mean. So what they're describing here is all of the data that is within 1 standard deviation of the mean. So 68% of your data, again, for part 4. Okay, next page there, page 300, question 5. The heights of a large sample of adults are normally distributed with a mean of 170 centimeters and a standard deviation of 8 centimeters. Within what limits do 68% of the heights lie? Okay, so our empirical rule tells us 68% of our data always lies within 1 standard deviation of the mean. So there's our mean is 170 centimeters. Our standard deviation is 8 centimeters. So 1 standard deviation above is 178 centimeters. And 1 standard deviation below is 170. Take away 8 is 162 centimeters. So 68% of the adults in this survey are between 162 and 178 centimeters. And then the second one says 99.7%. Well, we know from our empirical rule that 99.7% of data lies within 3 standard deviations of the mean. So that's 170 plus or minus 3 times 8 centimeters. Okay, 170 plus or minus 3/8 are 24. So that's a high of 194 and a low of 146. Okay, 170 take away 24 and 170 plus 24. 99.7% of our data lies within these 2 values, according to our empirical rule. Okay, we'll finish with question 14. Anna's marks for maths and history are given in the table. Find her Z-score or her standard score for each subject. Well, in maths, Anna scored 5% more than the average score. So 5 divided by 12 will give you her Z-score. 5 over 12 is going to be 42 or 0.42. And that's a positive Z-score plus 0.42. In history, Anna scored 8 below out of a standard deviation of 10. Okay, so she was minus 0.8 standard deviations, or 0.8 standard deviations below the average score. That formula, by the way, the standardizing formula, is given on page 34 in your log tables. So if you want to use that, you can say in maths, her score was 80, take away the average score of 75 divided by the standard deviation of 12, and that gives 5 over 12 or plus 0.42. The question then says, well, which subject did she perform better in? Now, in both absolute terms, she did better in maths, but also in maths, she was above average, and she was 0.42 standard deviations above average, whereas in history, she was below average, and she was 0.8 standard deviations below average. So the raw score by itself doesn't actually tell the whole story, and a standard score generally gives a better idea of how somebody performed relative to their peers. Part 3, Anna's friend Kira got a Z-score of 0.5. What raw score did she get? That is in history. So she was half of the standard deviation. If her Z-score is 0.5, she was half of the standard deviation above average. So that's 78 plus half of a standard deviation is 5. So she would have had a raw score of 83. Now, if you like algebra, the way you might do that is you say, well, Z is X minus mu over sigma. So her 0.5 is her raw score minus the average score of 78 over the standard deviation in history was 10. And solve that, multiply through by 10 there, you get 5 is X minus 78. 78 moves over, you get 5 plus 78 is her raw score, is 83. Okay, either way, you get 83% is her score in that one. Okay, so as well as making sure you got 1, 5, and 14 done into your copy, can I also ask you to go now and do questions 3, 4, and 13 on pages 299 to 302. All right, thanks, guys. See you next time.